Remainder estimate for the integral test. Suppose f of n equals a sub n, where the function f of x is continuous, positive, decreasing after some n terms. And suppose that the series is convergent, but we do not know what the sum is. If the remainder is the difference between the actual sum and the partial sum, then the remainder is always going to be between the two definite integrals. One go from n plus 1 to infinity, the other one go from n to infinity. And the actual sum, whatever it is between the partial sum plus the integral from n plus 1 to infinity of f of x dx, and the actual sum will be less than the partial sum plus the integral from n to infinity of f of x dx. For example, given the series 1 over n to the fourth power, find the partial sum s sub 10. So n in this case, in the theorem, n is 10. Then estimate the error using s sub 10 as an approximation to the sum of the series, using n equal 10 to give the improved estimate of the sum. Compare your estimate in part B using the exact value given by Euler, which is zeta of 4 pi to the fourth over 90. And then find the value of n so that the partial sum is within 0.00001 of the sum. First, we see that the partial sum s sub 10 is the sum from n equals 1 to n equals 10 of 1 over n to the fourth. The first term is 1 over 1 to the fourth. The second term is 1 over 2 to the fourth. The third term is 1 over 3 to the fourth. The last term, the n term, when n equals 10, is 1 over 10 to the fourth. So there are 10 terms total. And this sum is approximately 1.082037. Using the continuous function f of x equals 1 over x to the fourth, we know that it is decreasing because the first derivative is minus 1 x to the negative 5, which is minus 1 over x to the fifth, which is clearly negative because x is n and n go from 1 to infinity. If the derivative is negative, then the function is decreasing, but the function is the terms in this series. And so the theorem says that whatever the remainder is, it is going to be between the two improper integrals, 10 to infinity, 1 over x dx, and the other integral is 11 to infinity, 1 over x to the fourth dx. Notice that the sum or the area under the curve 1 over x to the fourth from 10 to infinity is more than the area under the curve 1 over x to the fourth from 11 to infinity. Evaluate the two improper integrals. We see that the left integral will give us 1 over 3 times 11 to the third power, and the right improper integral will give us 1 over 3 times 10 to the third power. And the remainder is between the two numbers. And so the remainder is less than 0.0003. The theorem also states that whatever the actual sum is, it is between the partial sum plus the integral from 10 to infinity of 1 over x to the fourth dx, and the partial sum, which is s sub 10, plus the integral from 11 to infinity of 1 over x to the fourth dx. But from part A, we saw that S sub 10 is 1.082037, and 1 over 3 times 11 to the third, which is the integral from 11 to infinity, is about 0.000250. This is less than the actual sum, and the actual sum is less than or equal. Now S sub 10 is still 1.082037, and the improper integral from 10 to infinity of 1 over x to the fourth dx is 1 over 3 times 10 to the third, which is 0.000333. And so we estimate that S, the actual sum, is between 1.082287 and 1.082370. If we average the two, then we will get 1.08233. Euler's gave us the actual sum, which is pi to the fourth over 90. In decimal, this is 1.082323. And comparing to the sum that we just estimated, we see that it is up by 0.00001. Lastly, find the value of n so that the partial sum is within 10 to the minus 5 of the sum. The theorem says that r sub n is less than or equal to the integral from n to infinity of f of x dx, and so r sub n is less than or equal to the integral from n to infinity of 1 over x to the fourth dx. And we don't know what n is. That's what we're going to find. Evaluate the improper integral. We see that this is 1 over 3n to the third power. And we want this error, this remainder, to be less than 0.00001. Solving for n, we will need n to be at least 32. The reason why the integral is 1 over 3 n cubed is that we take the limits at t go to infinity of n to t 1 over x to the fourth dx, and we see that this is the limit at t go to infinity of minus 1 over 3 x cubed. Evaluate from n to t. The antiderivative of x to the negative fourth is x to the negative 3 over minus 3. And so we take the limit at t go to infinity of minus 1 over 3 t cubed minus negative 1 over 3 n cubed. But as t go to infinity, 1 over 3 t cubed go to 0. And so we end up with 1 over 3 n cubed.